Okay, we are recording. Gonna just sort of have a bare introduction to rotational motion this week. And then Wednesday will be our last lecture. We'll have a review session for the test, the final test on, I'm hoping to have one Thursday or Friday so that you'll have the weekend to work on that stuff. And so before I start into the rotational motion, I just want to briefly summarize some of the one-dimensional constant acceleration equations that we have. And so this is going to be 1D constant acceleration. And something that we had in there was that we had a definition of average velocity, which ended up being delta x over delta t. We have instantaneous velocity, which we just don't put a subscript on. That would equal dx dt. And that would be the limit as delta t goes to 0 of delta x over delta t. So we have those things. And then we had equations that looked like this. We had x is equal to x naught plus v sub xt. And I'm going ahead and putting subscripts of x on some of these things. But that would be if we have no acceleration. If we do have acceleration, then what this might look like is x is going to equal x naught plus v naught xt plus 1/2 a sub x t squared. And we could also write an equation that has v sub x squared minus v naught x squared. And this could be v2 squared minus v1 squared or v final squared minus v initial squared. But it'll equal 2 times the acceleration in the x direction. Whoops, yeah, 2a delta x. And so that would be like x minus x naught for delta x. But it could be x final minus x initial or x2 minus x1. It's just the change in x that we're talking about while the velocity changes. So those are some of the one-dimensional constant acceleration equations that we used. We're going to do something similar for rotational motion. And for rotational motion, we're going to imagine have some kind of a rigid object that can rotate. And it's easiest if we think of a round rigid object that rotates about some axis. And we'll actually extend this idea to be looking at rolling motion some of the time. But for now, let's just imagine a rigid object that is going to turn through some amount, and we'll pick just some line that we could draw on that object. So this might be the initial position of that line. As it turns through some angle, that line might be over here. And I don't know where I put my, oh, there it is, my circle drawing thing. After this, I can draw better circles. But for now, we'll just go with that. And we can imagine that that line has turned through an angle theta. And so we'd have some sort of a displacement on for this line. And it turns out that every point along this line will have turned through the same angle theta about that center there. So that's something that's going to be a bit different. However, every point on the line does not travel the same distance. And that's because we're going to work with our radian arc length thing here. Okay, that'll sort of work. Yeah, that's good enough. let's suppose that this distance out to here is R1, and this distance out to that farther arc is R2. And both of them have an angle theta in here. Okay. Well, the arc length S1 here is not the same as the arc length S2 that's out there. And S1 is going to equal R1 times theta, and S2 is going to equal R2 times theta. The arc length that's traveled ends up being proportional to the distance away from the center of rotation. So that's something that we're going to have to keep in mind as we're doing some of these rotation things. Something may turn through the same angle, but the distance it actually travels can be much different depending on where it is. If something is just traveling in a little circle around here, it's not going to go very far compared to something that's way out here on the edge of whatever the round object happens to be. So we'll have that. Now, something we're going to be interested in almost immediately is how long it took to go through this angle change theta. And I might just call it delta theta after this. But we'll be interested in something like the change in theta divided by the change in time. Now, they introduced this way back when we were talking about centripetal acceleration, at least in the textbook. And I've seen a lot of people quoting equations that came out of that section or somewhere that were a little bit ahead of us at the time, but this is okay. Delta theta over delta t is going to be the average. Actually, I'll write it on here. Average angular velocity. Now, we're going to treat this kind of like one-dimensional motion, but whenever we talk about this, if something is going in the counterclockwise direction, we'll call it a positive angular velocity. And if it's going in a clockwise direction, we'll call it a negative angular velocity. And it's similar to the way when you measure angles off of the x-axis. If it's going counterclockwise, you call it a positive angle. If it's going clockwise, you call it a negative angle. And so we're going to use that same convention that they have in there. Now, we use a symbol for average angular velocity that's actually the Greek letter omega. And usually when I write W's, I go like that and make them all sorts of different things. When I write omega, I try to make it a little more curly Q-ish. And so that's what my omegas will look like. My W's are sometimes indiscernible, but hopefully you can figure out from the context which one is which. Now we'll have average angular velocity. We'll also have instantaneous angular velocity, and this will be the limit as delta t goes towards 0 of delta theta over delta t. And in calculus, you might just write this as d theta dt. So, and by now you've all done a quarter's worth of derivatives almost. And so that's the way that instantaneous angular velocity can work. Well, let's go ahead and take time derivatives of these two expressions. And if we do that, this one and that one, I would have ds1 dt. What that represents is the speed of a particle that's out here at the distance r1. And so I could call that v sub 1. Well, if I take the time derivative of that side, I'd have d by dt of r1 theta Well, the radius isn't changing. We're staying the same distance out there. So it can come out of here, and that will equal, let's see, R1, pull it outside the derivative, d theta dt. Well, d theta dt is just omega. And if I did the same thing for this, I'd get something that looked like V2 is equal to R2 d theta dt. And this is a connection between rotational motion and the one-dimensional motion of something traveling along there. And that is that the instantaneous velocity of something that's traveling along there, this is if we don't have, actually, it's no matter what is what it happens to be, but it'll just equal R omega. And so it's going to be proportional to how far out there the thing happens to be. So we've got a few connections between these things. And in fact, I could go to my 1D constant acceleration. And now let's look at rotational motion. And see what kind of things I can write down. Well, one thing I can write down is that the average angular velocity is going to equal delta theta over delta t. And the instantaneous angular velocity will be d theta dt. So parallels here, so hopefully that's not too bad. Well, what about something like this? If I have constant angular velocity, I can write an equation that's analogous to this. Instead of x, I'll have theta. Instead of x naught, I'll have theta naught, and it'll just be theta naught plus omega t. And so there's a nice little parallel thing that we've got. This is what would be the case if you have constant angular velocity. Now, I want to do a problem that automatically pulls in rolling motion, but we'll be doing rolling motion probably next quarter. I think we may start with a little bit of a unit on that. But anyways, imagine you have a wheel of radius r that rolls without slipping along a horizontal surface for a total of 10 rotations. Through what angle will the wheel turn in those 10 rotations? Determine that in radians. Well, if we draw a round thing here, let's see. Where did I put my scrap paper? Yeah, here's the center of the wheel. I'll just draw a relatively small thing here. And we imagine this rolling along. Okay, so we pick a point on the wheel, maybe this one that's in contact. As the wheel rolls through one rotation until this thing is back down here, what'll happen is every point on the circumference of the wheel, and I'm just going to have it roll right, that'll be a negative rotation most of the time, but we're going to be interested in magnitudes. As it does that, every point on the wheel will come in contact with the ground until we get over here, and we've got this thing sitting there again. So let's see, I don't remember which hole I used to draw this thing with, but let's pretend that it's that one and just hope it looks the same size. Yeah, not bad. Okay, so there it is. But anyway, in one rotation, the distance this thing will have traveled, if this is the radius, is going to be 2 times pi times r. That's the distance it travels, but it's done one complete rotation. And so in that one rotation, we get 2 pi for the angle through which the wheel has gone. But if you've got 10 rotations, your delta theta is going to be 10 times 2 pi, which is 20 pi. For every rotation, you'll have an angle of 2 pi turned. Through what distance will the wheel travel in that time? Well, if you look at this, we've got 2 pi r traveled in each rotation. If you multiply that by 10, you'll have 20 pi r. And that'll be the distance that the wheel travels. And I guess we could call it d is equal to that. That's how far the center of the wheel will go. In one rotation, it's 2 pi r. In 10 rotations, it's 20 pi r. If the wheel travels these 10 rotations in a time t, what is the linear velocity of the wheel? Well, this is just going to be v equals d over t, and that'll be 20 pi r over t. What about the angular velocity of the wheel? Well, the angular velocity is delta theta over delta t, or just t, and that's going to be 20 pi divided by t. Is there any kind of a relation? Let's see, what's the ratio of the linear velocity to the angular velocity? Okay, well, let's just take the linear velocity and divide by the angular velocity. And what I get is 20 pi r divided by t, and 20 pi divided by t. Everything divides out except the r, and you can write v is equal to r omega. This is kind of an interesting thing. When something is rolling without slipping, the translational velocity of the center of the wheel is just going to be r times omega. And so we'll be able to make that connection. Let's see, and the ratio of the linear distance traveled to the angle through which it turns, that would just be d divided by delta theta is also, we'll have 20 pi r over 20 pi, and that's just r again. So from that, we can get that the distance traveled is just going to be r delta theta. And this seems like a fairly simple idea, but it's nice to know what these things happen to be. Let's see. Well, the next question asks about something called angular acceleration. Okay, well, with this rotational motion, so far we've got angular velocity. Something I didn't write down here was that acceleration is equal to dv dt, or instantaneous, or average acceleration would be delta v over delta t. Well, I can have the same thing happening with angular motion. In this case, for the average thing, I would have delta omega over delta t. Oh, by the way, the units of omega are radians per second. We're going to be using radians in this unit when we study this rotational motion. And so we won't be thinking about degrees so much, just radians. Anyway, this would be average angular acceleration. In this case, we use the Greek letter alpha for that, and that'd be an AVG. In this unit, we're not going to deal with situations where we have non-constant angular acceleration. So we'll always just have constant angular acceleration, and that'll be d omega dt. So that's what angular acceleration happens to be. And that's a version of a Greek letter alpha. When we have that angular acceleration, we can write an analogy to this equation. Anywhere there's an x, replace it with theta. And if there's a v, we replace it with omega. We don't have to have subscripts of x on here anymore. If there's an a, we replace it with an alpha. So we would have theta is going to equal theta naught plus, let's see, omega naught t plus 1/2 alpha t squared. Oh, I forgot to give you another equation here, and that is that v sub x is going to be v naught x plus at. I can do something like that here too as well. I can say omega is going to equal omega naught plus alpha t. Okay, so we had a set of one-dimensional constant acceleration equations. We've got a similar set here. I didn't do this one yet, which I could. I can go omega squared minus omega naught squared will equal 2 alpha delta theta. Now, this equation's only good when you have constant angular acceleration. This one was only good when you have constant acceleration. So I may not have had them all listed in the same order, but I can at least write them like that. So let's take a look at another example problem. An electric motor rotating a workshop grinding wheel at a rate of 1 times 10, 1.00 times 10 squared RPM. By the way, RPM is actually a measure of angular velocity. It's not convenient units. We'd rather have it in radians per second, which we're going to, first thing we'll do is to convert that. But that's what an RPM level happens to be. So it's switched off and assume constant negative acceleration of magnitude 2.00 radians per second squared. So that's the unit that we'll use for angular acceleration. How long will it take for the grinding wheel to stop? Through how many radians has the wheel turned during that time? And we can figure out all of this stuff using those analogous equations here. But the first thing I want to do is to convert that angular velocity. So omega is equal to 1.00 times 10 squared. That's 100, but it's got sig figs. And it's revolutions per minute. Okay, a revolution is a kind of angular measure, but I'm going to have to convert units on here. And what I do is say I'll have 2 pi radians per revolution. And then I multiply that by also 1 minute over 60, whoops, make that 60 seconds. Talking right at the same time. So 2 pi times that is going to be 200 pi divided by 60. I probably won't leave this in terms of pi. So okay, I actually get 10.5 radians per second for that. So that would be our omega value, and that's actually omega naught because it's given there. Okay, how long will it take for the grinding wheel to stop? Well, one equation I've got is that omega is equal to omega naught plus alpha t. I don't know what direction it's turning, but if it's got a negative acceleration of that magnitude, then alpha is equal to minus 2.00 radians per second squared. And let's see, when it stops, omega is going to be 0. So I'll just go with that. 0 is going to equal 1.00. Whoops. Nope. omega naught. I changed the units on it. It's 10.5 radians per second minus 2.00 radians per second squared times t. And I just have to kick that across, and I'll have t is going to equal 10.5 radians per second divided by 2.00 radians per second squared. Okay, the radians divide out. I'll have 1 over seconds on top divided by 1 over seconds squared on the bottom, or flip it and multiply, and I'll have seconds squared per radian when I do that. And I'll end up with seconds for my units here. And 10.5 divided by 2 is probably 5.25 seconds. So that's how long it'll take to stop. So very much like solving the one-dimensional constant acceleration equations that we had. So that was A. Figuring out that. Part B, through how many radians has it turned during that time? Well, I've got choices here. I could do theta is equal to theta naught plus, which I could just call 0. Actually, I could use this equation. I know what the time is. I'm interested in what theta minus theta naught is, because that would be how many radians it's turned through. So that's one equation I could use. And keep in mind, L is negative. So I would end up with, and I'll just write the numbers down, but then I'll show you what else we might do. Theta minus theta naught will equal omega naught, which was 10.5 radians per second times t, 5.25 seconds, minus 1/2 times 2.00 radians per second squared times that time squared. Okay, or I could do this. I can say omega squared minus omega naught squared equals 2 alpha delta theta. Okay, let's see what happens with that one. Should get the same thing we'd have here. Here I'd see about 50 here. Let's see, 50 minus 25. It looks like somewhere in the neighborhood of 25 radians when we're done with this. Just quickly doing it in my head, but this is 0. Alpha is negative. I'd have delta theta is going to equal minus omega naught squared over alpha, which is minus 10.5 radians per second squared divided by alpha, which is minus 2.00 radians per second squared. On top, I'll have radians squared per second squared. On the bottom, I'll have radians per second squared. I'll end up with radians for units. By the way, a radian is just a placeholder unit, because the radian measure of an angle is equal to the arc length divided by the radius. And this has units of length. This has units of length. And so there aren't any units left when you have here. So a radian, it's like a placeholder unit, just to let you know that it's an angular measure of a particular kind, but it doesn't have any physical units left in it. Anyway, when I do that, I'll get something close to 50, which is about what or let's see, where did I estimate for here? This was about 50. Actually, I'm going to get, that's about 50. 10.5 radians per second. I'm not sure. Actually, about 25. I'd get about 25 for that. I better check this. Yeah, for this one, I get 55 radians. For this one, whoops, take that out. Okay, what did I do wrong here? Anybody catch it? Oh, I know what. I lost the 2 delta theta. That's the problem. So it's actually 27.6 radians. That's what's wrong. Yeah, that one didn't come out the same until I remembered it was supposed to have a 2 on there. Okay, so there's our first problem, actually plugging in some of this stuff. Okay, now we've got a positive angular acceleration. Okay, another grinding wheel. These are common things to have. I remember, I used to have a problem on a test about a radial arm saw, which is I don't know, you don't see many of them anymore, but there used to be a lumber yard down on Broadway in Moses Lake. It was out near the freeway. I think there's a church moved into that building now, but I bought some wood in there one time, and it was like a 16-foot piece of wood or something, and I needed 2 8-footers, and I couldn't get a 16-foot piece of wood home in the car. But this radial arm saw, it's the diameter of its blade must have been at least 2 feet. It was enormous. And the guy turned the saw on, cut the board, and then let the saw coast to a stop. And it probably took it at least 2 minutes before it stopped turning. So that thing had really good bearings on it and things like that. So it could have had a small angular acceleration. So anyway, but here we've got one that's a different kind of wheel. It's initial rest rotated for 8.00 seconds with a constant angular acceleration of 5 radians per second squared. It's then brought to rest with uniform negative acceleration in 10.0 revolutions. So that would not be quite as much. Determine the negative acceleration required and the time needed to bring the wheel to rest. Okay, well, let's first figure out how fast it's going after those 8 seconds. So I would say omega is going to equal omega naught plus alpha t. It's initially at rest, so that's going to be 0. And this will equal 5.00 radians per second squared times 8.00 seconds. And this would end up being, I think I can do that in my head, 40.0 radians per second. And radians per second squared times seconds, one of the seconds will divide out and you'll have radians per second. So there we have that thing. Okay, then it's brought to rest in 10.0 revolutions. Determine the negative acceleration required and the time needed to bring the wheel to rest. So this will be like our omega naught. Okay, and we'll have, for this second part, omega is going to equal omega naught plus LT, but we don't know alpha or T in this case to stop this thing. But we do know that it takes 10 revolutions to stop. Well, there's another equation, and that is that, oh, I know this is 0 at the end, but I can also say omega squared minus omega naught squared is 2 alpha delta theta. Okay, and I know that it goes through 10 revolutions. Delta theta, I could write it as 10 revolutions, but that's not going to help me. I need radians. And so I just multiply by 2 pi radians per revolution, and I get 20 pi radians. So that's what delta theta is. This one is 0 at the end. This was, I had 40 radians per second to start with. And so I'm just solving for alpha now. So alpha is going to be minus omega naught squared over 2, got the 2 this time, delta theta. So minus 40.0 radians per second squared divided by 2 times 20 pi radians. When I'm all the way done here, let's see, the top will have radians squared per second squared. If I divide that by radians, I'll have radians per second squared, which is what I expect for an alpha. This is going to be 1600 up here divided by 40. So it'll be 40 divided by pi, around 13, I think, but let's check it. So I like to estimate what the numbers are going to be before I do them, because if I punch it in wrong and end up with something haywire, this will be a way of checking it. 40 pi. Yeah, I get about 12.7 minus 12.7 radians per second squared. And I guessed it was going to be about 13, so, or estimated. So that's alpha. That's the negative acceleration required. The time needed to bring it to rest. Well, now I can use this equation. I can say 0 equals omega naught plus alpha t, or t is going to be, kick that across, it'll be minus omega naught divided by alpha, which is 40.0 minus radians per second divided by minus 12.7 radians per second squared. I think I'm going to get pi for this thing. Let's see. Imagine that, 3.14 seconds. And that's just a coincidence because of the way they've got all these 8s and 5s and 10s and things like that combined to make everything else divide out. But that was just coincidence. Anyway, it would take about 3.14 seconds to stop that grinding wheel. So that was all there was to it. Let's see, an automobile accelerates from 0 to 30.7 meters per second in 6.03 seconds. The wheels have a diameter of 0.422 meters. What is the angular acceleration of each wheel? Well, a little while back, we made note of the fact that there's the center of a wheel. Now, we have to be careful. They gave us the diameter, not the radius, but we can figure that out easily. The radius is going to be 0.211 meters. And so we'll have that. For a point out here on the rim of the wheel, the instantaneous velocity v is equal to r omega, but it turns out this is the same relation that exists between the speed of the center of mass, the center of the wheel, and the angular velocity. So I can use this in two different ways here for when I have pure rolling like this. Oh, something we didn't do yet. Turns out the linear acceleration is equal to r times the angular acceleration as well. And we get that by taking the time derivative of both sides of this equation. dv dt is a, d by dt of r omega. Again, the r is constant. We can pull that out and we'll have r d omega dt, and that's what alpha is. So we can get all of these things by knowing about derivatives. So, well, shoot, if we figure out the linear acceleration, we'll have the other one. So a is equal to, we're assuming constant on there. It's going to be dv dt, or delta v over delta t. And so 0 to 30.7 meters per second sounds like 30.7 meters per second is delta v. The time is 6.03 seconds. So the linear acceleration is good practice to do this again because the final's coming up. 5.09 meters per second squared. And then the angular acceleration, alpha is just going to be a divided by r. Here's a place where it seems like things divide out. 5.09 meters per second squared divided by the 0.211 meters. And if you think of this as meters divided by 1, you'd end up with, in this case, alpha equaling 5.09 divided by 0.211. For a number, I get 24.1. But unit-wise, I'll have meters per second squared divided by meters over 1, or flipping that up, I'd have times 1 over meters. And the meters divide out, and I just have per second squared. But remember that radian is just a placeholder unit? That's what we'll have. Meters over meters is what a radian is. This is radians per second squared. Actually, feet over feet could be a radian as well. Inches over inches, any unit of length divided by the same unit of length could be what a radian happens to be. But I know that I'm going to be getting an angular acceleration here. And so that's what the angular acceleration of each wheel happens to be in this case. So sometimes you may have to have things disappearing, but just from the context, you know that it's going to be radians per second squared, or radians per second, or radians, something like that. You have to kind of invent those units back in. And we can do that just because the radian doesn't have any actual physical dimension to it. Ooh, are we already there? Yeah. This is a rotational motion problem that's kind of an astronomy one. It's sort of an interesting thing. The pulsar is a rapidly rotating neutron star that emits radio pulses with precise synchronization, one each pulse for each rotation of the star. There was an interesting article in the, just in the news sometime in the last year. I can't remember exactly when it was, but people who study gravitational waves, which are things that were discovered down at LIGO at Hanford. The first discovery was announced, I think, in 2017. But anyway, they were studying pulsar radiation coming through space and found out that traveling through gravitational waves can tweak the period of this stuff. So that's kind of a neat thing, but that would have to worry about that on this problem. We've got enough complications as it is. Anyway, the period T of rotation is the time for one rotation. It's found by measuring the time between pulses. So at present, the pulsar in the central region of the Crab Nebula has a period of rotation of T equals 0.033 seconds, and it's observed to be increasing at the rate of 1.26 times 10 to the minus fifth seconds per year. Well, that's not much of a change here, but what is the value of the angular acceleration in radians per second squared? Well, we're going to have to figure this out here. That period T is equal to, well, in this case, 0.033 seconds, but that's something that we want to have. But how does that depend on something like angular acceleration and things like that? Well, let's go to omega is going to equal how long it takes for one rotation divided by that period. And so that's what omega happens to depend on. And so we can figure out a value for omega here. This is kind of amazing, actually. Oh, something else that's amazing. The frequency of rotation, and we use a lowercase f for frequency, not a capital F, so as not to confuse it with force, but it would be 1 over that period there. The frequency, this is seconds per rotation. The frequency is rotations per second. And that could be, well, yeah, just rotations per second. It's the reciprocal of that anyway. So 1 divided by 0.033, turn on the calculator first. It's about 30.3. Actually, we only have 2 sig figs, but write it this way. 10 to the first rotation per second. Okay, this pulsar is a neutron star. They typically have a mass of about a solar mass or a few solar masses. If they get too many solar masses, they don't become neutron stars, they become black holes instead, the remnant of the supernova, the star that produced the supernova. But this thing is turning 30 times per second. Okay, and so that's something with a mass equal to that of the sun and turning that rapidly. When pulsars were first discovered, they didn't know what they were. And they thought that they picked up this thing that was just producing, I think the first one was like, well, I don't remember what the frequency was, but it was just something that kept producing these radio pulses. And it was just like clockwork. And at first they thought it maybe was an low Earth satellite. They were discovered shortly after the launch of the first satellites. but it didn't make much sense. And then they noticed that, oh, I think the people that discovered it, Jocelyn Bell was the woman who discovered them. She gave them the moniker or the name LGM1 for the first pulsar they discovered. And LGM stood for Little Green Men. And it was just a joke that maybe it was some sort of extraterrestrial intelligence that was doing this. And then they studied it more and they found out that the pulsar signal would disappear at certain times. Radio telescopes they were using had no way to determine the direction from which it was coming, but it would disappear for certain periods every day. But then they noticed that the signal from this thing actually came onto the antenna that they were using or the telescope 4 minutes earlier every day. And it turns out the Earth does not take 24 hours to turn on its axis with respect to the stars. It takes 24 hours or 23 hours and 56 minutes and a few seconds. And so that told them that it was a radio source that was way out somewhere in the vicinity of the stars. And eventually, with other radio telescopes, they figured out that it was actually coming from the center of the Crab Nebula, which is in the constellation of Taurus in the night sky. So a lot of weird history about this stuff. But anyway, they figured it was something that was rotating to be that steady. And at that time, a neutron star was only a theoretical prediction, but for a thing of one solar mass to spin that rapidly, it had to be something like a neutron star, because a neutron star is actually held together not by gravity or the electromagnetic force, but by the strong nuclear force. And that's the only force that's strong enough to hold together an object that large when it's spinning that fast. So pretty crazy, lots of different physics and astronomy in here. So what's the value of the angular acceleration in radians per second squared? Well, that's going to depend on angular acceleration in this case is going to be delta theta over delta t. The delta t is, or delta omega, excuse me, getting my Greek letters mixed up. Excuse me. Delta omega over delta t. We know that in 1 year, its rotational period drops by 1.26 times 10 to the minus fifth seconds. And so somehow we're going to have to work that into the delta omega up here. The year down here is going to have to be the number of seconds in 1 year. Well, we can figure that out pretty easy. Delta t is going to be 1 year is about 365.25 days times 24 hours per day times 3,600 seconds per hour. And if you multiply all this stuff together, you get something that's approximately pi times 10 to the 7th seconds. Let's check that out just to be sure. Anyway, 365.25 times 24 times 3,600. Yeah, I get 3.16 times 10 to the 7th seconds. So delta t equals 3.16 times 10 to the 7th seconds. But if you used pi times 10 to the 7th, you wouldn't be far off. 2 parts in 316. But now we somehow have to figure out something like this. Well, we'll have an omega final is going to equal 2 pi over t final, and omega initial is going to equal 2 pi divided by t initial. Well, the only difference between the two is that t final is going to equal t initial plus that 1.26 times to the minus fifth seconds. And I'm going to call that delta t. Excuse me, got a scratch in my throat. All right, well, let's see if we can make any sense out of this. Alpha is then going to equal delta omega will be one of these minus the other one. Actually, it's going to be negative, but that's okay. I'll have 2 pi over t final minus 2 pi over t initial. I'm going to divide that by the delta t, which is the number of seconds in a year. But let's wait and see if we can make some sense out of this stuff first. I'd like to get a common denominator on these things and multiply them together. So common denominator would be t final, t initial. And this is just kind of a thing that I try when I've got expressions that are fractions like this. So if I multiply the first term by 2 pi t initial on top and bottom, minus the second thing times t final top and bottom. So I'd have 2 pi t final over t initial t final. I'll end up with 2 pi times t initial minus t final divided by t initial times t final. And I forgot, I've still got a delta t on the bottom down here. And let's see, what can I do? T initial minus T final is actually going to be, T final is bigger. It's going to be the negative of that delta T that we've got there. So I'll have minus 2 pi delta T, delta capital T, divided by T initial, T final. And this, if I added this onto it, it's not going to show up in the number of significant figures I've got. This T initial, T final is essentially T squared, capital T squared, at least to my ability to measure it. And then on the delta lowercase t down there, I've got the other thing. Let's see, what's the rate of angular acceleration? How many years from now will it stop rotating? Okay, I'm running out of room, but that's all right. Yeah, I'll just finish off part A here. I'll have that alpha is going to equal 2 times pi times 1.26 times 10 to the minus fifth seconds. And then on the bottom, I'm going to have t squared, which is 0.033 seconds squared times, let's see, lowercase delta t, which is 3.16 times 10 to the seventh seconds. So all kinds of weird stuff going on this problem. Unit-wise, these seconds will divide with those seconds, and I'll end up with per second squared, but I've got 2 pi radians on top. And so that'll be radians per second squared. That'll be good old alpha. And I need some kind of a weight to set on here. Okay, stay. divided by okay, this is not a very large, whoops, this has a minus sign on it. Minus 2.3, and I've only got two significant figures, times 10 to the minus ninth radians per second squared. So that is a pretty small angular acceleration. And I think students might have to leave, but I'm just going to keep going through on this thing and solving the rest of this problem. B asks, if its angular acceleration is constant, how many years from now will the pulsar stop rotating? Oh, good grief. Well, I can do this. I can say omega equals omega naught t plus, omega naught plus alpha t. It's going to equal 0. And I can figure out the time for this, and then I'll have to do some work to convert it into years, but t will equal just omega naught divided by alpha, or minus omega naught divided by alpha, but alpha is negative. Anyway, omega naught is 2 pi divided by the period, and then I divide that by alpha with the minus sign. So I'll have minus 2 pi divided by capital T is the period, so 0.033 seconds, and then I multiply by that minus 2.3 times 10 to the minus ninth radians per second squared, and I'll end up with seconds times radians per second squared is radians per cent. These are radians on top. I'll end up with seconds. And that 10 to the minus ninth on the bottom is going to guarantee that I end up with quite a few seconds, I guess. So let's see what this ends up being. Whoops. Divided by. This isn't as long as I thought. I get about 8.3 times 10 to the 10th seconds. That seems too short. I may have to work through this again because I'm not positive that's right. If I multiply that by 1 year over 3.16 times 10 to the 7th seconds, I only get about 2,620 years, which doesn't seem all that long to me. I mean, for astronomy stuff, it's not a very long period of time. I wonder if I did that all right. I may have to check my math on this angular acceleration stuff to make sure that I have it correct there. But that's question B. And part C, I'm going to go ahead and keep working on it too. Part C is it originated in a supernova explosion seen in the year 10,054. What was the period T of the pulsar when it originated? and assume constant acceleration, angular acceleration. Well, the period is increasing at the rate of 1.26 times 10 to the minus fifth seconds per year. How many years ago was 1054? Well, this is 2023 minus 1054. And we get 969 years. So if we have a constant angular acceleration like this, period now will equal the period then plus how many years it's been, 969 years, times that 1.26 times 10 to the fifth seconds per year. So the period now is the 0.033 seconds equals the period then plus this. Oops, that's a -5 on there. Plus 0.012. Actually, we could say 122 seconds, but it's not going to matter because I've only got out there for that. So, and I get that the period then was 0.021 seconds. So it is getting longer, and it was much more rapid in those days, although nobody knew about it in those days. Interesting thing about the discovery of the Crab Nebula, it was a supernova explosion of a star, and is visible in the daytime sky for months. And it was reported by Chinese and Japanese astrologers who in those years would be employed by whoever was in charge in their country, and made to make predictions based on the stars and things like that. But there is no mention of it in Western literature. That means in European civilization literature, or not even in the Arabic countries, but mainly in Europe. The civilization had fallen so far after the collapse of the Roman Empire that an event this noticeable, visible in the daytime sky for months, wasn't written about. So it's kind of a sad commentary on the state of European civilization at that time. Actually, I'm not sure. There may have been some mentions of it in Arabic astronomer writings, but not in Western Europe. Okay, well, I'm going to stop with that one, and I'm going to go back and check my numbers on this just to make sure that they're correct, because it doesn't seem like all that long a time before it'll stop rotating. So how do I stop rotating? I forgot how. Stop the share, end the meeting, and end the